In the last video series, we took a look at Newton's second law applied to rotations. And so now we're going to go ahead and take a look at the case of being in equilibrium. So the conditions for equilibrium are that the acceleration of the system is equal to 0, and also that the angular acceleration is equal to 0. So this does allow for the possibility of an object that's moving at constant speed while rotating at a constant angular velocity as being considered to be in equilibrium. As a practical issue, though, usually things are in static equilibrium, where we can say at least to some observer or other, things aren't moving at all. So we'll just focus on static equilibrium in the xy plane. So what the acceleration condition is going to mean is that the sum of forces in the x and the sum of the forces in the y both have to be 0. So we'll just write it that way. Sum of forces in x is 0. Sum of forces in the y direction is 0. And the requirement that the angular acceleration be 0 by Newton's second law applied to rotations will mean that the sum of the torques is also 0. Now we've already visited this a bit when we were looking at the teeter-totter problem in the previous video. But I want to revisit it just one more time to show how we can take advantage of the fact that the thing isn't rotating to make the problem easier to do. And I'll mix it up a little bit from the last time. So this time, I'm going to say that we know that the teeter-totter is 3 meters long. Before, we basically kind of had it that the teeter-totter was whatever length was required. But here, let's say it is 3 meters long. And again, it'll be the same deal. We're going to put a big kid on one side of the teeter-totter. We'll say mass of 50 kilograms, just like before. And a little kid on the other side of the teeter-totter. He's not quite so happy about it because they know that they're going to get launched into space, or they're afraid of that anyway. There we go. Well, again, just to make life a little less bad, we'll make the teeter-totter itself massless. And so the two things I want to know. So I want to know how hard, and we'll say, and just like before, we'll make the lighter kid 25 kilograms. So now here, I'm interested in knowing how hard is the fulcrum pushing up. And also, I do want to know how far from the big kid should I put the fulcrum so that the game is fair and the teeter-totter balances. So I'm just dimensioning the distances from the big kid to the fulcrum. We'll call that L1. That's what we need to know. We know L is 3 meters. And we'll say that the distance from the little kid to the fulcrum is L2. And by looking at the diagram, we can work out that that's equal to L minus L1. Okay. So since we've already drawn the extended free body diagram for this, let's just go ahead and do it quickly here. So big kid, little kid, and we will, and this is what's called an extended free body diagram because we're drawing a little cartoon of the thing. So You can go ahead and draw in the forces, just like we did before. So last time we found that there were two forces of gravity, Fg1, Fg2, and a normal force. And we're going to do this problem twice, just to show the benefit of being a bit clever about your choice of free bodies, or sorry, of your choice of rotation axes. Oops. There we go. So first we will do it by making the reasonable seeming choice of putting the axis of rotation where the fulcrum is. So, all right, let's go ahead and dimension out our lever arms here. So what we've got is, this is R1 perpendicular, that's equal to our L1, and this here is our R2 perpendicular. It's equal to L2, which is equal to L minus L1. There we go. So the conditions of equilibrium say that the sum of the forces in the x direction has to add up to 0. Well, okay, everything's happening vertically. So, all right, it's true, 0 equals 0, but it doesn't help us much. All right, let's look at the y direction. So the sum of the forces in the y direction also has to be 0. So we've got the normal force acting straight up, and we've got the two gravities acting straight down. So we put minus signs in front of the gravities to indicate that they're going down. So this gives us that the normal force is equal to Fg1 plus Fg2. So this is M1g plus M2g, or if you prefer, M1 plus M2g. All right, so we can put in the numbers. 50 kilograms for the big kid, 25 kilograms for the small kid, 9.8 newtons per kilogram. You get 735 newtons. So the fulcrum has to push up with 735 newtons of force to keep the teeter-totter from crashing through it. All right. And so then just to repeat off our analysis we did before for getting our distance L1 right here, which is R1 perpendicular. Let's balance the torques. We'll have a torque due to gravity from the big kid trying to twist the whole thing counterclockwise about this axis right here. So when we say sum of torques equals 0, the counterclockwise torque will be equal to Fg1 R1 perpendicular. And we will have a torque due to gravity from the small kid trying to twist it clockwise. So that'll make it negative. So that'll be minus Fg2 R2 perpendicular. And then since the normal force's line of action goes right through the axis of rotation, the torque due to the normal force about this choice of axis is 0. So I will just say plus the normal force times our normal perpendicular, but our normal perpendicular is 0. All right. So Fg1 is equal to M1g. R1 perpendicular we called L1. That's what we want to find. Fg2 is M2g. And our 2 perpendicular we worked out was going to be L minus L1. And since we want to find L1, that's probably the most profitable way to write it. Okay. So first thing we can do is we can divide both sides of the equation by g. So that would drop the g's here and leave us with a 0 over g here. So it's still 0. So this will give me m1, L1. And then I'm going to distribute the m2 across this. So this will be minus m2L. Then minus minus is a plus m2L1 equals 0. All right, so we'll gather our knowns. So we'll have m1 plus m2 times L1 equals m2L. And then finally, L1 equals m2 over m1 plus m2 times L. And now we can put in the numbers. 25 kilograms over 50 kilograms plus 25 kilograms times 3 meters is, like we saw before, 1 meter. Okay. So that's one way you could have done it. I think it's worth doing this again. And this is because when you're in static equilibrium, like we are right here, where the teeter-totter isn't rotating or anything like that, you can say, well, we picked this fulcrum as our axis of rotation because, well, there's a fulcrum there, right? But if you think about it, since you're not rotating, you could just as easily say that instead of that you're not rotating about an axis right here, that, for instance, you're not rotating about an axis here, or up there, or down there, or anywhere. If you're not rotating, you are free to choose the axis about which you are not rotating. So how could this help us? Well, this can help us because we asked how far away from the big kid should we put the fulcrum. So there's a natural dimension in the problem. And sometimes when you've got a natural place to measure from, it's more convenient to put the axis of rotation about that point. Then that's going to make our R1 perpendicular equal to our L1, which we don't know. But now the lever arm for this force of gravity about this axis, our R2 perpendicular, is just playing the entire length of the teeter-totter, which we already know to be 3 meters. So this will clean up the algebra quite a bit. Now this will be at the cost of having to calculate the normal force. But if you've got multiple forces involved in the problem, it might be faster to calculate the normal force anyway, and then put the axis around the natural 0 in the problem. A classic on this is literally problems that ask things like, where should I hang the weight on a meter stick to get the weight to balance? Well, you're talking about a mark on the meter stick, so put your axis of non-rotation, if it were, at 0, because that's where you should be measuring from. You'll be faster and you'll make fewer algebra mistakes. So this bit right here of calculating the normal force is still the same. So I'm not going to repeat it here. I'll just paste it in. But now let's go ahead and look at the sum of the torques. So we're going to say the sum of the torques. Oops, here we go. The sum of the torques is equal to 0, but now we're doing it about this leftward axis. So first off, the first thing we notice is that the torque due to gravity now from the fat kid is 0. And this is because the lever arm for the big kid's force of gravity is going right through the axis of rotation. Now, but now we have a non-zero lever arm for the normal force. So you win some, you lose some. So we can go ahead here and we can say, well, we had FG1 times R1 perpendicular, but R1 perpendicular is 0, so that term went away. Now, when I look around this axis, the normal force is trying to twist the teeter-totter counterclockwise around this axis. So the normal force will be exerting a positive torque about this axis right here. So we'll say plus N times R1 perpendicular. And then here, the force of gravity from the small kid is trying to twist the whole system clockwise. So that's going to make it negative. Now here, since my axis is here, my R2 perpendicular is now the entire length. But we'll just start by saying minus FG2 R2 perpendicular equals 0. Okay, let's put in the things we have. So the things we have are the normal force. This R1 perpendicular is the L1 we're trying to find. Minus force of gravity 2 is M2G. And this R2 perpendicular is now just L, the length of the teeter-totter. So we get 0 over here. So then we can just immediately solve L1 equals M2G over the normal force times L. And we can go ahead and put in our numbers. This is going to be 25 kilograms times 9.8 newtons per kilogram over 735 newtons times 3 meters gives us the same 1 meter we found before, but let's look at the algebra. Before, to get L1, we had quite a few lines of algebra before we could get to the 1 meter. Here, it's basically one line and we're done. So we did have to find the normal force, just like we did before. But even if it was a problem where we wouldn't have had to find the normal force, it might have been faster to just go ahead and find it anyway, because usually balancing forces in the y direction is very straightforward. Okay. So let's go ahead and do a little more complicated example. Let's say that you are hanging a sign off the side of a building. So you're going to have a hinge right here. And let's just say the sign is right here. Mass of the sign is 10 kilograms. And then there's also a guy wire that we're taking back to the wall. So what I want to know is, here, let me also put in some dimensions. Let's say this distance here is 3 meters. So that will make this distance here 4 meters. And I'm going to say 4 meters to the center of the sign. And this is because the force of gravity is going to act at the center of the sign. So I'm dimensioning it out to that point there. And then, let me redraw my guy wire. I want my guy wire to match that spot there. There we go. So that'll make that 5 meters just in case we need that. 3, 4, 5 right triangle, the interior angles are 37 and 53 degrees. And we'll call this 37-degree angle theta. So what I want to know is, what is the tension in the guy wire? And I want to know the magnitude and the direction of the normal force that the hinge applies to the massless rod here. Now you might think at first, wait a minute, why could it point in any arbitrary direction? And that's because if you look at the typical construction of a hinge, you have a pin and you have a follower sleeve around it. So the normal force is going to be exerted so the sleeve is kind of free to slide around the pin. And so say the pin might end up over here. And then the normal force being exerted would be perpendicular to the surface right there. So in principle, the normal force could point any which way. It'll turn out in this problem, once we actually solve for it, that the normal force points straight to the right, but let's just say we didn't know that right now. All right, so I'm just going to go ahead and draw my forces in here. I've already got my normal force drawn in. I was really close to drawing in my force of gravity from the sign, and we will add in my force due to tension right here. Okay. Now we're going to need the x and the y components of each of these forces. Now, since I don't know the angle that the normal force is pointing yet, my strategy here is I'm just going to say this is nx and that's ny. I'm going to solve for them both, and then this will let me figure out magnitude and direction. Similarly here, the line of action for gravity points straight up and down like this. Oh, sorry. I'm getting just a bit ahead of myself here. Let's go and pick an axis of rotation. Since, again, it's not rotating, we're free to choose the axis about which it is not rotating. But we can make the torque equation much simpler if we choose our axis of rotation to be right here at the hinge. Why is that? Well, it's because then the normal force's line of action passes through the axis, and that will make the torque due to the normal force 0. And since we don't know the normal force, that gets rid of it in the torque equation, and we will just be left with a torque equation that has a torque due to our unknown force of tension and our force of gravity. So here I'm going to do two different ways of expressing the torque just because it's convenient. So here for gravity, what I want to think about is my line of action for gravity. And it just points straight up and straight down forever. And so it turns out that this distance, 4 meters here, this is the R perpendicular for gravity. And let's make that a more readable color. There we go. So this is my lever arm for gravity. Now for the tension, what I'm going to do is I'm just going to say this distance here is R for the tension. Instead, I'm going to be more interested in expressing what is the tangential component of the tension. So Ty here, which is equal to T sine theta, this is also the tangential part of the force due to tension, because this is the piece here that's actually trying to make the whole assembly spin around the axis counterclockwise. All right, So with all of that into place, let's go ahead and express our forces, our force laws, and our torque. So the force laws are going to give us sum of Fx equals 0. So what have we got? Well, we have the x component of the normal force presumably acting to the right. And to the left, I have the x component. Oops. I have the x component of gravity, or sorry, of tension here, Tx, which is equal to T cosine theta, acting to the left. So this will be minus T cosine theta. That has to equal 0. All right. Sum of Fy equals 0. What's this going to give us? Well, we have Ty, we have the normal, we have Ny acting up, potentially. We've also got a y component of gravity, or sorry, of tension acting up. So this would be plus T, and the y piece was T sine theta. Then we have gravity from the sine acting down. That equals 0. And then finally, we need to look at our sum of torques. So sum of torques equals 0. Because of how we chose our axis, there is no torque due to the normal force. So the counterclockwise piece we have here will be this tangential component of tension times this distance r here. And then the clockwise piece is what gravity is attempting to do. So that's r perp gravity times Fg. That has to equal 0. All right. Now it turns out these two r's are the same. So r, and then we said that T tangential is the same thing as Ty is T sine theta. So RT sine theta minus R Fg equals 0. Hey, this is awesome. So what I've got is RT sine theta equals R. Then the force of gravity is mg. And the r's cancel. That's cool. We get that the tension is just equal to the force of gravity over the over sine theta. All right. So this will be 10 kilograms times 9.8 newtons per kilogram over the sine of 37 degrees gives me 163 newtons. Cool. Now, let's go revisit that y equation of motion. So that y equation of motion said the y component of the normal force plus T sine theta minus Fg equals 0, but we literally just saw here that these two are equal and cancel. So in this particular case, what we get is that the y component of the normal force equals 0. So now we know that the direction is, it has to be to the right. You could be cagey and say it's horizontal, but look, the only force that's got anything horizontal is tension. We know it's going to the left, so we do know that the normal force is pointing to the right. So we worked out that the y component of the normal force is 0. So that will now let me say that the normal force points pure. Oops, let me do a more contrasting color. No, I don't want that one. That one. So we now know that. No, it didn't help much either. Fine, that one. Okay, that's as good as it gets. So we now know that the normal force actually points straight to the right. So we can revisit our x equation of motion, which said that the x component of the normal force minus t cosine 37 degrees equaled 0. And we just worked out that the x component of the normal force is the entire normal force. So the normal force is equal to t cosine 37 degrees. So that's 163 newtons from the first part times the cosine of 37 degrees gives us 130 newtons. Cool. Alrighty. So in the next video, we'll take a look at a couple of additional considerations in thinking about equilibrium. We will explore conditions for stability and balance, and we will also introduce the elastic force or the spring force. Catch you in the next one.